Right, okay. So last lesson we did a number of different tests looking at the reactions of halogenoalkanes, and the one that I'd like to focus in on, well, two of them actually, were the reactions of the halogenoalkanes, firstly with sodium hydroxide and secondly with water. Now, the reaction with water, you may have overlooked this one as in this case, the reagent that you used, the particular mixture that you were reacting with the sodium hydroxide, was silver nitrate solution. Now, the thing to understand there is that silver nitrate was not directly reacting with the halogenoalkane. It is, in fact, the water that was present in the solution that's reacting. Now, in both of the cases, you had the same observation as an outcome of this. A precipitate was formed with the silver nitrate solution that was used. In the case with the sodium hydroxide reaction, you had to, after carrying out the reaction, you acidified the solution to neutralize any remaining sodium hydroxide, and you saw a silver halide precipitate result. In the case of just reacting the halogenoalkane with the silver nitrate solution, you again saw a silver halide precipitate. Now, this tells us that in both of these cases, there is an inorganic side product of halide ions, as these are the things that are reacting with the silver ions within solution to produce the silver halide precipitate. So you have Cl minus being produced from a chloroalkane reaction. You've got bromide ions being produced from an alkyl bromide reaction, and you have iodide ions being produced by an alkyl iodide reaction. Now, again, you could actually see that it was these particular halide ions if you watched for the color of the precipitate very, very closely. Of course, it took a little bit of a while to develop properly, but you would have seen, for example, with the alkyl iodide, so the iodoalkanes, you would have developed eventually a yellow colored precipitate when there was enough of it there. Now, this tells us that during the reaction, that was occurring with hydroxide or with the water. The halogen, which is present in the halogenoalkane, was being displaced from the molecule, or as we might call it, being substituted. So this brings us on to a second type of reaction generally that we see within organic chemistry. We've talked about addition reactions. So addition reactions when you have a reaction where all of the atoms in the reactants are incorporated into one product. Now we've got a new type of reaction, which is a substitution. And this is where an atom or a group of atoms within a reactant is substituted or replaced by another group of atoms. Now, that simply describes what is happening to the molecule itself. It doesn't necessarily give us an idea of how this is going on, and in order to do that, we need to look more carefully at the at the halogenoalkanes themselves, and to have a look at their general structure and try to deduce how they are going to react. Now, in this case, I'm going to represent the halogen atom itself as an X. This is done standardly within organic chemistry. So do look out for that notation in future. So the defining feature of the halogenoalkanes, the functional group, is where you have your carbon bonded to the halogen. Now, let's have, of course, the carbon will be bonded to other groups, but we're going to just focus in on this section of the molecule to start off with. Now, halogens tend to be of high electronegativity, and therefore we end up with a polarization of this bond. The halogen is going to end up as delta minus, and the carbon is going to end up as being delta plus. This means that the carbon itself is actually electron deficient. In a way, its nucleus is more exposed as electron density is pulled away. And therefore, the carbon in halogenoalkanes is susceptible to what we would call a nucleophilic attack. So by this new type of reacting species called a nucleophile, which is something unlike an electrophile, which is attracted towards regions of high electron density, nucleophiles are attracted towards regions of positive charge, regions of low electron density. Okay, so let's note that down. So nucleophile, reacting species attracted to regions of low electron density. Nucleophiles will often have negative charge, but not always. The key thing that a nucleophile needs in order to effectively act as a nucleophile is a lone pair. So they will pretty much always have lone pairs, and they are sometimes negatively charged. Now, I say they mostly have a lone pair because in some cases things that we consider to be nucleophiles have, instead of a lone pair of electrons, have some other form of a available electron pair. So for example, a pair of electrons within a pi bond can allow something to act as a nucleophile because they can be transferred relatively easily. Okay, so having talked about that, how do we actually end up with the reaction which occurs with the halogenoalkane? So we know that they're going to attract things called nucleophiles, species with lone pairs, and we end up with a substitution where the halogen atom becomes displaced from the molecule as a halide ion at the end. So let's have a look at a simple case of the reaction of let's go for iodopropane and sodium hydroxide. and we'll do 1 iodopropane. Okay, so just as you've learned with the alkenes, we don't need to draw out the entirety of the organic molecule as a displayed formula. We just need the area around the functional group to be displayed. So we're going to start off with our CI, and then we've got H and H, and we have then the rest of the molecule. So in this case it's propane, so that's going to be a C2H5 group. Now there's literally no way of rearranging that C2H5. It has to be a CH2CH3 group, so we can just leave it as C2H5. There's no ambiguity there. In larger groups, you might have to give the structural formula format of the rest of that in order to make it 100% clear, but for 1-iodopropane, that's not necessary. Right, we're going to label onto this molecule then, as we did in the reaction of the alkenes, our partial charges. So we've got our delta positive carbon and our delta negative iodine. And right, one thing to note here, and I should have brought up earlier, that this is sodium hydroxide in the aqueous state. This is very important. Okay, there may very well be some ethanol being present to help mix together the 1-iodopropane with the sodium hydroxide, but there has to be water present for this particular reaction to occur. It favors the action of the sodium hydroxide as a nucleophile. And of course, it is the hydroxide ion which is acting as a nucleophile in this case. It is a species which has a low pair of electrons. It also has a negative charge, which allows it to act very strongly as a nucleophile. Now, your sodium hydroxide, negatively charged, is going to be attracted to the delta positive carbon within this molecule. And so it's going to be drawn in to attack that. And as the hydroxide ion, which is negatively charged, is brought in towards the delta positive carbon, electrons in the carbon iodine bond are going to become further pushed away, and so that leads to the carbon becoming more delta positive, which again pulls on the lone pair of electrons even more, and eventually we get a movement of electron pairs which we can represent with curly arrows like so. Okay, and this leads then to a one-step mechanism where the I minus is completely displaced. So we see electrons go onto the iodine completely, so it becomes I minus. And the OH becomes bonded onto the organic molecule. The 1-iodopropane has now been converted into propan-1-ol, and we've got I minus. Now, of course, in both cases, we have the Na plus present as a spectator ion. Okay, sodium hydroxide is used in this case so that the sodium can dissociate from the OH minus. It's a soluble compound, but the sodium itself is a spectator ion. It doesn't really affect the reaction itself, and it just ends up as part of the side product of the reaction. So you end up with sodium iodide here. Right. Okay. So yes, so we produce the sodium iodide side product. This is still dissociated within solution, and of course the iodide is what ends up precipitating with the silver ions that are present. Now this is essentially a separate reaction that we are using to identify the fact that a nucleophilic substitution has happened with the halogenoalkane. And it's really important to understand that this is a separate reaction going on here. Okay, the nucleophilic substitution of the hydroxide with the halogenoalkane starts off with a colourless organic liquid, and it ends up with a colourless organic liquid. Our addition of the silver nitrate into this whole process is just to identify the fact that iodide has been displaced from the reaction due to the substitution, and therefore we are using that silver in the silver nitrate to produce that precipitate that tells us that is the case. Right, okay, so that's the nucleophilic substitution between 1-iodopropane and sodium hydroxide. Now, what about the reaction with water? Because clearly that also causes a reaction too. Just adding in the silver nitrate solution to the halogenoalkane also resulted in some sort of substitution because, again, we had that silver halide precipitate. So, let's just start off with a quick look at water as a nucleophile versus hydroxide as a nucleophile. So if we were to draw out just a very quick simple dot and cross diagram for hydroxide, it's going to look like this. And note here that because hydroxide is an ion, there is an additional electron which has been gained from elsewhere, which is what gives it that -1 charge. So the oxygen has 3 lots of lone pairs around it, which each can allow it to act as a nucleophile. Now, in the case of water, we do not have an ion, we've got a molecule. And the dot and cross diagram looks like this. Now, here we've got 2 lots of lone pairs, which again are available to allow the molecule to act as a nucleophile. Now, it turns out that water is not as good a nucleophile as hydroxide is. First thing that you might jump to is the fact that there is that negative charge on the hydroxide, which of course is going to allow it to become more easily attracted to regions of low electron density where there is a partial positive charge, where the nucleus is exposed, hence the nucleophilic aspect of it. But secondly, the other reason that the hydroxide will be more nucleophilic is actually because its lone pairs are more unstable and higher in energy. Now, why is this? Well, simply because there are 3 of them rather than 2. If you remember from electron pair repulsion theory, lone pairs of electrons, because they're only pulled towards one atom, they are more electron dense and therefore more repulsive than bond pairs of electrons. So around the hydroxide, there is a higher degree of repulsion than around the water molecule. And this higher degree of repulsion means that the lone pairs on the hydroxide are higher in energy than the lone pairs of the water molecule. This means that the lone pairs on hydroxide are more likely to go towards forming a bond, towards undergoing a reaction than the lone pairs in water are. Okay, so summary, hydroxide is the better nucleophile, and this water is a poor nucleophile. Right, now that all said and done, let's go on to have a look at how the mechanism for the reaction between water and a halogenoalkane differs from the reaction between a halogenoalkane and hydroxide ions. Okay, so let's go with 2-chloropropane and water in this case. Now, this reaction is referred to as a hydrolysis reaction because water is being used to break up an organic molecule, hence hydrolysis. Right, okay, so 2-chloropropane this time. So we've got our carbon, and let's add on our Cl, and this time the Cl's added at the secondary position, so we've got a CH3 group on either side of that carbon, which is bonded to the Cl, and we've got a H. And again, as always, we want to label delta minus and delta plus. Right, now in this case, our nucleophile is water, so I'm going to draw that out as just H2O. And we've got our relevant lone pair, which is always shown. And just as for the hydroxide, we undergo a nucleophilic attack. The lone pair moves towards the delta positive carbon, and then we have the breaking of the carbon-chlorine bond here, shown by electrons leaving from the bond and going onto the delta minus chlorine. Again, one step, and this is going to get us to this format here. Don't forget that carbon. So H and our CH3 has been shifted around, and now we have the OH2 bonded on like this, and we've got our Cl minus. Now, of course, Cl minus can't be a product on its own. You can't just have something with a negative charge just existing on its own. But this time we started off with two molecules which are uncharged, and now we've got an ion here which is uncharged. So actually there's a problem here, because there should be a positive charge somewhere else. Now, to identify where the positive charge is, we need to look to our mechanism and see where electrons are moving away from. And we see electrons moving away from this carbon, but they're also moving towards it. So that's not where the positive charge is building up. The only atom that has electrons moving away from it and not towards it is the oxygen. So the oxygen has a formal positive charge here. Okay. Now, if we remember, this turns up with the reaction of bromine water with the alkenes, and this is a very similar intermediate to that formed there. Now, this is very unstable because you've got the positive charge on the oxygen, electron deficient oxygen, so this is going to break down very quickly by the oxygen just simply pulling electrons away from whichever atom it is easiest to do so, and in this case it's going to be hydrogen. So we show electrons from the oxygen-hydrogen bond being pulled just straight onto the oxygen, and then that brings us to our product. Now you will note that just as for the reaction with hydroxide, our product is again an alcohol this time, because we started off with 2-chloropropane. This is going to be propan 2-ol. The side product, though, is different. We have lost a H plus from the water, and we've got Cl minus from the 2-chloropropane. So this is giving us hydrochloric acid as a side product. And again, the chloride ion can go on. If you've got silver nitrate present within the mixture, this will react with Ag plus, and that proves that the substitution has taken place. So, key difference here to the reaction with sodium hydroxide is the fact that firstly there's more steps here. The OH2 plus group has to break down in order to give you the OH group, and also the side product is a little different as well. You get hydrochloric acid instead of a salt of hydrochloric acid, a chloride.